Every single day, municipalities across the country are forced to process millions of tons of wastewater sludge and organic bioscraps. For city planners, this relentless flow of wet, heavy material represents a massive disposal liability that drains local budgets. For decades, scientists have proposed biological solutions to this exact problem. Anaerobic digestion, breaking down organic waste without oxygen, and cultivating microalgae were supposed to act as the ultimate municipal recyclers, turning toxic waste into clean energy and valuable fertilizer. But the chemistry rarely cooperates at scale. This split bar chart compares the actual biogas yield of raw municipal sludge against its theoretical potential. The actual yield stalls out because raw sludge contains too much nitrogen and not enough carbon. That imbalance severely limits the microbial activity required to produce combustible gas. The math gets even worse on the algae side. Because microalgae grow in highly dilute suspensions, drying biomass requires burning immense amounts of fossil fuel. As you can see here, the cost to dry the material completely swallows any financial value the bioenergy provided. Relying strictly on natural biology without precise engineering intervention leaves cities with systems that cost more to operate than they generate in return. To make waste-to-energy viable, the facility must aggressively manipulate both the chemistry and the physical infrastructure. The first intervention introduces a heavily managed agricultural crop into the waste stream: wetland cattails, or Typha latifolia. Cattails are dense with lignocellulosic carbon. When harvested and fed directly into the anaerobic digester alongside the municipal sludge, they instantly correct the system's nutrient imbalance. The carbon from the plants binds with the nitrogen from the waste, driving a 40% boost in overall biogas production. The facility then scrubs and upgrades this expanded gas output into renewable natural gas. Once injected into the grid, it qualifies for high-value Federal Renewable Identification Number, or RIN, credits. This becomes the primary cash engine for the entire operation. But we still have to manage the raw liquid digestate left over from the process. If you pump this directly into an algae pond, the microalgae will die. The liquid is too turbid for sunlight to penetrate, and it contains toxic levels of free ammonia. Instead of massively diluting the digestate with fresh water, the system routes it through a specialized pretreatment settling tank. This step drops the suspended organic solids out of the liquid, clarifying the water before it ever reaches the engineered ponds. The algae can now freely consume the dissolved nitrogen and phosphorus. By artificially correcting the carbon deficit in the digester and clearing the turbidity in the ponds, the facility turns a strict disposal liability into a high-yield resource loop. To solve the massive fossil fuel drying deficit, the facility abandons bulk water harvesting. Sensors constantly monitor the ponds, deploying mechanical skimmers to peel off only the thick, concentrated top layer of algae. That wet paste is then routed away from fossil fuel burners and into a retrofitted 40-foot Conax shipping container. Surrounded by angled glass and polished steel reflectors, this container operates as a passive industrial solar kiln. In this cross-section of the Conax kiln, you can see how the system manages heat. The incoming solar rays dry the biomass on the racks, while simultaneously charging a thermal battery at the base of the unit. This floor is filled with a phase-change material called erythritol, which melts as it absorbs the intense daytime heat. As the sun sets and the ambient temperature drops, the erythritol slowly crystallizes back into a solid. As it changes phase, it releases latent heat upward through the chamber. This allows the kiln to maintain internal temperatures between 80 and 150 degrees Celsius, actively dehydrating biomass long after dark. Stripping away the cost of purchased natural gas or electricity for drying completely reshapes the economics of the facility. The harvested algae and excess cattails finally retain their commercial value. Yet all biological systems share a fatal vulnerability: winter. Freezing temperatures halt the photosynthesis of both the algae and the cattails, threatening to shut down the nutrient recovery loop. The facility anticipates this by shifting its operational mode. The massive reserves of cattails dried in the solar kiln during the summer are now steadily fed into the anaerobic digester, ensuring the renewable natural gas production never drops. Meanwhile, the nutrient-dense liquid digestate completely bypasses the frozen outdoor ponds. Instead, the liquid is pumped into an indoor chemical extraction system. engineers introduce magnesium chloride and zeolite, which bind instantly with the dissolved nitrogen and phosphorus. This chemical reaction pulls the nutrients out of the water, precipitating them into a highly concentrated, solid agricultural fertilizer. This seasonal pivot from biological filtration to chemical extraction ensures the facility can accept municipal waste and generate distinct revenue streams 365 days a year. What begins as raw municipal sludge and organic waste enters the facility and exits as clean water, renewable grid energy, and premium agricultural commodities. For investors and city councils, this translates into two distinct financial pathways. Pathway 1 is the biofertilizer route. This is the lower risk, lower complexity model, where the dried, highly nutrient-dense algae is bagged and sold directly into commercial agriculture as a soil amendment. Looking at the financial dashboard for this first option, the total capital cost sits at $8.46 million. By stacking the revenue from the renewable natural gas, the chemical winter fertilizer, and the summer algae sales, the facility achieves simple payback in just 2.8 years, generating a 431% return on investment over a 15-year life cycle. Pathway 2 is the biodiesel route. This requires building additional extraction infrastructure to press the valuable lipids out of the dried algae, refining them into a liquid transportation fuel. This dashboard shows the heavier upfront requirement. The capital cost rises to $10.96 million. Even with the added infrastructure debt, the high market value of the extracted biodiesel pulls the payback period to a rapid 3.6 years, easily clearing a 300% return over the same 15-year timeline. By systematically breaking the chemical limitations of digestion and the physical costs of drying, cities no longer have to view wastewater as a burden. The engineering exists today to turn their costliest liability into their most reliable civic asset.